ratings company. Currently, he's an independent consultant working with clients like Dataspora and Revolution Analytics. He blogs regularly about big data and analytics, and so I encourage you to seek him out after the talk. So we're going to switch the mic here. We'll see if the folks in the back can hear okay. We may adjust the volume a little bit. You guys may want to move a little closer if you're having trouble hearing.
Funnily enough, this is the second time someone got 100 questions in 3 days. Because it used to be there and it's not there now. So we have to, someone removed it and we have to go back and add it. So it's on our to-do. Hey, you winner.
Does it work? So I'm here to talk about a set of packages that allow our developers to work with Hadoop. The project itself is called the complex of the packages called as a project. This is an open source project spearheaded by Revolution Analytics. A quick presentation about Revolution Analytics. They build themselves the RHadoop of R. So they back an open source product with services, an assured build, additional testing, add-on products, packages, some proprietary, some open source. I was pretty sure I didn't need to introduce Hadoop to this audience, but I'm not sure about R. So just quickly, it's a language for statistics. I think introduced around 1996, derived by a much older S+ with some important changes. S+ is proprietary. Some people consider it initial a dedicated language. Some people consider it general purpose. I won't enter the discussion, but it has received lots of attention. Some people call it the de facto standard for computational statistics. I tried to back that assertion with some hard facts. It's actually really hard. People don't even know. If you should compare it with Spotfire, which is a really interactive package, or you should compare it with Python, which is a general purpose language. But if you add a bunch of libraries, then Python can use for data analysis. So it's questionable, but it was covered in the New York Times, so that must mean something, right? If you want to see some numbers, R4Stats has some numbers about how R is catching up, a number of publications, number of companies using it, so on and so forth. So why the combination with the two? When you have two big stars like Angelina Jolie and Brad Pitt, you want to see them together, right? You want to see the babies. And so for the same reason, R coming from more the statistics community, known for its expressiveness, the richness of the libraries. On the other hand, Hadoop provides scalability. Let's put them together and let's see if we can create a better tool. This is part of a general trend to allow analysts to use interpreted language or dynamic higher level, whatever you want to call them. And so it's not that it doesn't break new ground, but it comes from the statistics side. So Hadoop is a complex project. As I don't know, satellite or sub-projects, exactly how to call them. So we started with 3. One is Hadoop HDFS, the package that we offer to access the service of HDFS is RHadoop. It has kind of 2 layers, the byte level, bytes and bytes, bits and bytes, and the higher level, move files around, list directories, make a copy, and so on and so forth. Then there is HBase, the Hadoop database, and the package is called HBase. And it offers an intuitive interface to the main features. You query for range of records, you return the data frame, which is the standard tabular data structure in R. You can write, you can create a table, you can do a number of important operations. And finally, there is Hadoop MapReduce, the package. I really asked for the shorter name, so it's called RMR. And it's the one I'm working on specifically, and I want to talk about this one in particular tonight. So the first, I thought maybe I don't need to do, there won't be too many statisticians in the room. I don't need to do the statistic R side kind of pitch. But maybe there are, and maybe other people talk with statisticians and we want to repeat a similar pitch. So this is, there goes the argument. First, if you want to play with the big toys, pretty much the standard is Hadoop. So this is the most concrete route for a statistician to access the biggest data sets. The other argument is, well, I don't want to deal with data sets, huge data sets. My data sets are medium. So I have the reserve argument is the speed of a single core is not increasing anymore. It stopped around 2004. I realize that some people don't know that yet. Tell me, oh, everything gets always better. The new laws applies to everything. At least one thing is now getting better. I'm getting older. But other things are not getting better, like the speed of the single core. So, and that's the blue line there. You see the flight is around 2004, just days before it's overhead. So, if you don't pick up some parallel programming tools, you're stuck there. It's like 20 years from now, it's like having a Commodore 64 to do your analysis, and that's not gonna. Unless you are uninterested in computation and statistics, you have to upgrade your tools. Then the third argument, we really try to make it like R, as close as possible in syntax and semantics without creating confusion, because there are differences. But really a natural extension to the language. I was listening to somebody presenting, I forgot the name unfortunately, presenting Scolding, which is a library for Scala, a MapReduce library for Scala, and they say, we just copy the iterator library. Makes a lot of sense, right? Everybody knows it, and you establish the similarities, some differences, and you build on some common accepted knowledge. So, MapReduce abstract ideas exist in functional programming since, I don't know, how long ago, and they exist in R, implemented sequentially in the interpreter. So we follow that analogy. Provide primitives that look and feel like the built-in ones, and so that every good R programmer can pick up this new tool very easily. Finally, it is just a library. Of course, working for Evolution Analytics, we kind of didn't have a chance. We had to write something for R, but we didn't want to create a new language because it's very difficult to create a new language. It takes a decade to learn a new language according to Norvig, and it takes time to create a community. The libraries take decades to put together. So it really, if you can pull it off with the library, you should pull it off with the library. And there aren't even, you don't need to patch interpreter. There's no special trick. It is just a library. So you can use your tools, existing libraries, the ID you're used to, and so on and so forth. So now going to the other side, if you're not invested in R yet, how does tool fit within all the other tools? Should you pick it? Of course, it's a more difficult decision. It's a bigger step. I try to group some of the MapReduce tools that I know of, I mean, languages or libraries that I know of. In this diagram, vertically, you go kind of from the higher level to the lower level of abstraction or expressiveness. And there's another divide, the tools that expose directly the MapReduce API, and the tools that try to hide it and provide something kind of based on it but above it. So cascading is in Java, which is kind of lower level, but hides MapReduce pretty much from you. And Dumbo is in Python, but exposes MapReduce directly. I think the main reason why we decided to embrace MapReduce instead of hiding it is that tools like Pig are not general purpose. I think it's a big statement. I think at this point it's quite clear from a lot of discussion that have been going on the big mailing list and forums. So it's not something that I say just in kind of the recited way, it's something that I heard from them. I don't know if the same is true for Hive. I haven't seen a lot of algorithm research done in SQL, but I think the same could be true. Instead, from MapReduce, we have a huge number of examples and even theoretical results that support the idea that you can write any algorithm, any parallel algorithm in MapReduce. So we decided to provide an abstract interface that hides the details, but still offers direct access to MapReduce. So there is one call and one job. I don't exclude in the future we try to do also some of the transformations that merging of jobs that other tools offer, possibly as a separate problem. So this is it, the main call of the whole package. It's called MapReduce, of course. It has an input and output, and it takes two functions. So the input, in the simplest case, is a valid HDFS path over multiple ones, or you can even pass directly the output of another MapReduce job. We made up things so that you can concatenate them very easily. The output will be another HDFS path, or you can just skip it, and MapReduce will find a place to store your data and return an object that encapsulates that location, but kind of hides the boarding part from you, so you don't have to pick up a name, you don't have to delete it when you're done. It's kind of managed. So we call them big data variables. They are stubs for the data. You can move them around, assign them, but you can't really do, you can't see inside other than by using the primitives of the library. And then the map function is an ordinary R function. This is kind of in opposition to another package. Actually, the first package that offers a bridge between R and Hadoop, RHadoop, where you have to pass unevaluated expressions, and to parameterize those expressions, you have to use expression substitution. Those are kind of interesting, but esoteric features in R that very few R programmers I know of. I know that I had to learn them just to learn this library. So we try to be, we look at the apply family of functions in R. They take a function, so we should take a function, and that's how we do it. And the same for the reduce function. If you go more in detail, how do you write the map? It's really the simplest possible R function. It's a function of two arguments, the key and the value, straight from the MapReduce paper. And for instance, you can evaluate, test a condition on the key, and return the same key value, in this case, with the constructor key value, or return nothing. In that case, you're skipping the record. And the third possibility is that you could return a list of key value pairs if you, in other application, you can return them. I forgot the beautiful animation of the input. The reduce function, again, a function of two arguments. The second, in this case, is a list of all the values associated with the same key. This is in keeping with the original MapReduce paper, but again, a departure from this other library where you're not guaranteed that all the keys are going to be there in a single call. And I guess it's a little bit of a trade-off between, oh, I don't want to bust the memory limits versus try to do things cleanly. So it's, it's not obvious which one to do, but we just try to stay plain vanilla. And sometimes that list is going to be very long, and it may be a problem. And the same, you return a key value pair, 0, 1, or more. So an interesting thing, what do we mean by integrating with the language? I think the most interesting aspect and a little more technically challenging for us to implement is to make the scoping, scope rules of R work across machines. So if you want to parameterize a MapReduce job, how do you do it? Let's say you have a condition, which is some function that's very trivial function, then there's a boolean, and you write a MapReduce job, it takes some input, and then the map function evaluates that condition, and if it's true, it returns the key value, otherwise it doesn't. And the interesting part is that that condition, that variable condition, is available inside inside the map function. And that's normal R. That's how it should be according to lexicon scoping. But what happens is that that function is executed on 10 or 100 different machines in different interpreters. So behind the scenes, we're taking an environment, we're serializing, deserializing on the other end, and so that you have the impression that scope rules are upheld. And it gives you the simplest way to parameterize a MapReduce job according to an absolutely standard R programming idiom. So the other element of the API that you really need to know is a bridge between the big data side of things and the small data, so in memory and on disk. And so there's a pair of function called from the FS and to the FS that implement this bridge. You call them at your own risk, so you can't call from the FS on any file and get away with it. You have to be sure that the data has been reduced enough for you to do that. And when you call from the FS generally to inspect the data, decide on the next steps to doing the computations or to do visualization, for instance, or to report on the data in general. And the 2DFS is used mostly for not for the real deal, but for debugging, testing, and it's intended to use for all the test suite is written using 2DFS. It's a great helper. So now, a comparison with Hive, going into a terrain where we know RMR is going to come out at a disadvantage. I just want to show that it's not so bad. This is a query that everybody has seen in one shape or another. A group records by one attribute and count them while making sure that another attribute is not repeated. So enclosing a distinct clause on a different attribute. And the RMR version is a composition of two jobs. So you see there is an internal job and an external, one job nested beside the other. And it's very simple. You just give one job, the return value of one job in input to the other one, as if they were regular in-memory functions, but they are just passing stubs around. The data is somewhere else. But the good thing is that you don't need to constantly think about that. And the inner one, which of course I executed first, takes care of the selection of the attributes and the uniqueness condition. And the outer one does the counting. And you see the MapReduce functions are not even one line, they're half line, and fairly simple. But still, you know, for what it does, Hive is absolutely a great tool. There is more than API, meaning that probably the Hive interpreter does some optimizations, like turning on the combiners, that if you don't think about, RMR won't do for you. So it's very easy to turn on the combiner, but here I didn't do it, and so if you don't do it, you pay the price for it. On the other hand, it would be very easy to build an abstraction on top of this R expression, whereas I don't know exactly how to do abstractions in Hive, because R is a language, and there's all the tools of modularity and abstraction built in that the serious language has. So now, a slightly more complicated example. I'm not going to go through all the lines, but just give you an idea of what the plain vanilla k-means implementation looks like. It's just two functions. The first, there's no MapReduce, it's just controlling the iteration behavior. And the inner one starts a MapReduce jobs that turns a set of points and the set of candidate centers into a new set of candidate centers and replaces the old one. And it's 25 lines of code. And the interesting thing is that the way that the set of centers is passed from in-RAM to the job is exactly what I described before. No fuss, you don't have to do anything, no set, no get, no nothing. And just following scope rules, it's going to show up when it has it. And the same is true for the number of centers there. And here you see the use of from DFS. Once the new set of centers is ready, it gets brought into memory and then broadcast again to the nodes via simple scope rules. And that's kind of similar, if you're familiar with a similar idiom to website joins. So one side of the join is broadcasting, the other becomes the input to the job. And it's absolutely trivial to express that. So by comparison, I want to show you k-means time in peak. And again, we're just going to look at the big picture. So first, where did I find this? It goes on the Hortonworks blog, probably slightly dated now. I chose it not because I want to pick on the Hortonworks guys, but because I'm sure that if they did it, they put it on the blog, it's probably close to the state of the art. So first of all, it's 3 pages, 1, 2, 3. We navigate 1, 2, and 3. And second of all, why the 3 colors? Because it's 3 languages. It's mostly Python. It's not in pig. The pig is there in green. This is all Python. And there is the need for an additional EF that's implemented in Java. I think now you can try also this last page in Python with the latest improvements here. So one example doesn't prove anything. The 2 algorithms are not absolutely equivalent. Let's not even start talking about performance. I have no idea how much slower the app version is. But just to give you, just to create some curiosity, it's a fifth of the code. It's incredibly trivial. Where I have an audience that knows R, I just go through every line of code, and it's a pleasure to discuss how k-means work in a distributed, in a parallel fashion. So just a few resources to wrap it up. The project is hosted on GitHub. It's called RHadoop. It's licensed with the standard Apache 2.0 license. The documentation is split between the package, included package help and the GitHub wiki. You can just start a new issue if you have a question that you are willing to share with the other users. And if you don't want to, if you like confidentiality, then there is an email address, and the project lead is the CTO of Revolutionary State Champagne. And with that, we have to take your questions.
Any questions from out there in the audience? Going once? Going one question.
There's the open source data mining software.